Right now, somewhere in the world, a factory is printing circuits onto a piece of silicon features so small they are measured in billionths of a meter. The chip being made will end up inside an iPhone, or an NVIDIA AI processor, or a guided missile system. And here is what almost nobody knows. None of it, not the phone, not the AI, not the weapons, can be made without one machine. A machine built by a company most people have never heard of, in a country most people would never guess. A machine that took decades and billions of euros to bring into existence. A machine that pushed its creator to the edge more than once. A machine so valuable that when the world's two superpowers realized only one company could make it, they turned it into the center of a new kind of war. The global chip war did not begin with a country. It began with a machine. This is the story of that machine and the quiet Dutch company that accidentally became one of the most strategically important businesses on Earth. The bottleneck. To understand why this machine exists, you need to understand a promise the chip industry made to the world and almost couldn't keep. In 1965, Intel co-founder Gordon Moore observed that the number of transistors on a chip doubles roughly every 2 years. More transistors meant more power, smaller devices, lower costs. That observation became Moore's law, and for half a century, it held. It's the reason the phone in your pocket has more computing power than the systems that sent Apollo 11 to the moon. But Moore's law has an enemy: physics. Making a chip is essentially photographic printing. You shine light through a stencil onto silicon, and the light draws the circuits. The smaller you want the circuits, the shorter the wavelength of light you need. And by the early 2000s, the industry had pushed its best light source, deep ultraviolet, to the edge of what physics allows. The next step required a new kind of light entirely: extreme ultraviolet EUV. A wavelength of just 13.5 nanometers, more than 10 times shorter than anything used in production before. There was just one problem. EUV light is so energetic that almost everything on Earth absorbs it. Glass absorbs it, lenses absorb it, even air absorbs it. Shine EUV light across a room, and it simply vanishes before reaching the other side. To use this light, someone would have to build a machine that creates it from plasma, guides it through a near-perfect vacuum, and focuses it using mirrors polished to atomic precision. In the late 1990s, much of the semiconductor industry believed that machine could not be built. Engineers inside the industry had a nickname for it: a science project. Not a product, not a business, a science project. And in semiconductors, that phrase is not a compliment. It means the idea may be brilliant, but it may never leave the lab. One company decided to find out. The machine. The company was not in Silicon Valley, not in Tokyo, not in Seoul. It was in Veldhoven, a small town in the southern Netherlands. ASML, a 1,984 spin-off from Philips that started with around 30 employees working out of a modest building on a Philips campus. In 1997, ASML joined an American-led research consortium to explore EUV alongside Intel and US national laboratories. What followed was one of the longest, most expensive engineering gambles in industrial history. Roughly 2 decades of development. Billions of euros in research spending at times, a major share of the company's entire revenue poured into a machine that did not work yet and might never work. Competitors looked at the same problem and walked away. Nikon, the Japanese giant that once dominated this industry, eventually stepped back. Canon stepped back. ASML kept going, even when the program threatened to drag the whole company down with it. By 2012, the EUV program was consuming enormous amounts of cash with no finished product in sight. So ASML did something almost unheard of. It turned to its own customers. Intel, Samsung, and TSMC, fierce rivals who agreed on almost nothing together, invested billions and took significant stakes in the company, funding the research directly. They had little choice. If ASML failed, Moore's law stalled, and the entire industry's future stalled with it. The machine they finally built defies belief. Inside it, a droplet of molten tin about 30 micrometers wide, smaller than a grain of pollen, falls through a chamber at 70 meters per second. A laser strikes it twice. The first pulse flattens it, the second vaporizes it into plasma hotter than the surface of the sun. That plasma emits EUV light. Mirrors then guide the light mirrors so smooth that if one were scaled to the size of a country, its largest imperfection would be measured in millimeters. This sequence happens tens of thousands of times per second. Each finished machine contains around 100,000 components, sourced from a network of roughly 800 suppliers. Shipping a single system can require dozens of freight containers, multiple cargo planes, and a fleet of trucks. Installation takes months, handled by teams of specialized engineers. And the price? A standard EUV system costs hundreds of millions of dollars. The newest generation High-NA is reported to cost around $400 million each. When production EUV machines finally reached chipmakers in 2017, 2 decades after the serious research began, Moore's Law had been given more time. But something else had happened, something nobody had planned. The entire future of advanced computing now flowed through a single company, in a single town, in the Netherlands. ASML hadn't just built a machine, it had built the world's most valuable choke point: the chip war. When one machine becomes essential to the future of technology, access to that machine becomes a matter of national power. China understood this early. By 2018, China was spending more money importing semiconductors than importing oil. In Beijing, chips were never just a tech issue, they were a strategic vulnerability. The government poured tens of billions into building a domestic chip industry, but there was a wall they could not climb. To make the most advanced chips, you need EUV, and only ASML makes EUV. Washington saw this same chessboard and moved first. The logic was simple: no EUV machines, no advanced chips, no cutting-edge AI, no next-generation military systems. Advanced lithography sales to China had already been restricted since 2019. Then, in October 2022, the United States launched the most sweeping semiconductor export controls in its history. And although ASML is a Dutch company, American pressure reached The Hague. The Netherlands agreed to keep ASML's most advanced machines out of China entirely. Here's the remarkable part: China had never received one of ASML's advanced EUV machines. Not one. The ban wasn't reversing something, it was preventing a future. Washington understood that the moment China could print chips at the most advanced nodes, the balance of technological power would shift in ways that would be very hard to undo. The fallout turned a quiet engineering company into a geopolitical battlefield. The Netherlands found itself squeezed between its closest security ally and a market that had become one of ASML's largest sources of sales. Then came the kind of story ASML was never built for. The company disclosed that a China-based employee had stolen proprietary technology data. Dutch media later reported links between the case and Huawei. For ASML, it was more than a leak. It was proof that the machine had become something larger than a product. It had become intelligence, leverage, and national strategy compressed into one supply chain. China's response has been to spend whatever it takes to build its own version of the machine. Experts remain deeply skeptical. The technology rests on decades of accumulated knowledge spread across hundreds of suppliers, and that kind of knowledge cannot simply be copied. But the race itself is now redrawing the map of the global economy. But here's the twist: ASML builds these machines, it doesn't use them, it sells them. And its most important customers for the most advanced systems sit nearly 10,000 kilometers away on a single island, Taiwan. TSMC has installed more of ASML's cutting-edge EUV machines than almost any company on Earth, packing them into the factories that print the world's most advanced chips. And that creates the strangest geometry of all. The most advanced chips in the world are not made in Washington or Beijing. They are made on that same island, one both superpowers cannot afford to lose. The most important machines on Earth, built in a quiet Dutch town, end up inside the most contested supply chain on Earth. And that is why the next chapter of this story leads directly to TSMC. Why this matters to you. Here's the part most coverage misses. This is not a story about governments. It's a story about your daily life. If chips are the oil of the 21st century, a comparison now made by economists and military strategists alike, then EUV machines are the refineries. Without them, the oil stays in the ground. Your phone, your car's driver assist system, the AI you talked to this morning, the server holding your savings account data tonight, all of it runs on chips that exist only because of EUV lithography. And we already know what happens when this supply chain stumbles. In 2021, a chip shortage caused by delivery disruptions. Not lost factories shut down car assembly lines across America. New vehicle wait times stretched past a year. Used car prices jumped so sharply, they moved national inflation numbers. A chip shortage does not stay inside a factory. It shows up as a higher car payment, a delayed phone launch, a more expensive laptop, a weaker supply chain for every country that depends on it. That was the cost of a hiccup. A genuine rupture in the advanced chip supply chain, a conflict over Taiwan, an escalation of the export wars would make 2021 look like a rounding error. Governments know this, which is why they're spending like it's wartime. The CHIPS Act committed $52 billion to rebuild American chipmaking. Europe is spending billions more. Nations are now treating semiconductor supply chains the way they treated oil fields in the last century, as strategic assets to be secured at any cost. And every one of those new factories on every continent will need machines from the same single company in the Netherlands. The reveal. Remember that factory from the beginning of this story, the one printing features measured in billionths of a meter? The chip it's making will end up in someone's pocket, maybe yours. And the person holding it will never know that the device in their hand exists because of a decades-long gamble made by a company in a small Dutch town, a gamble that came close to failing more than once before it changed the world. The chip war is not really about chips. It's about which nation controls the systems that power the future AI. Autonomous weapons, quantum computing, digital infrastructure. Every one of those technologies runs on advanced semiconductors. And every advanced semiconductor traces back to one machine, from one company, that no rival has yet replicated at scale. ASML never set out to become a weapon of foreign policy. It set out to solve a physics problem most people said was impossible. It succeeded, and in succeeding, it created the single most important choke point in the modern economy. The most powerful systems in the world are often invisible. They don't appear on the news. They sit in clean rooms, printing the future one wafer at a time. And sometimes, the entire balance of global power depends on a machine almost nobody has ever seen. That's not noise, that's a capital signal.